Okay, today we're just doing a few add-on notes from what we did previously with the voltage. First thing we're going to talk about is what current is. So you might have heard current, and we're going to be using this over the next little while. And what we're talking about is the flow of electric charge. So if we have parallel plates that we've been talking about lately, so let's suppose we have a parallel plate, one plate's positive, one plate's negative. And if we put a positive charge in here, we know that it's going to move across the plates due to repulsion and attraction and so on. So we know that that's going to have voltage, right? There's going to be energy as that thing moves, so we can calculate how much voltage there is in those plates. But anytime we have a moving charge, we say that there's also current. So current, instead of it just being one charge moving and figuring out the speed or things like that, what we're talking about is we're assuming that we have an infinite number of charges. So in this case, if I had a whole bunch of positive charges, one after the other, and they're all going to move, our current then is how many coulombs per second flow. So it's sort of like a speed of the charges moving. Not speed per charge, but sort of the rate or how fast they're moving across one after the other. So for current, the formula we use is I is for current, and it's just charge divided by time. So it's a pretty easy formula. And our I is our current, and Q is our charge in coulombs. Time would be in seconds for our basic unit, so our current then is coulombs per second is the technical version. But just like other units, we call current, we measure it in amps, named after Ampere, is sort of to honor him. So amps is the exact same thing as coulombs per second. So that's just a little key thing to remember. So if we had positive charges, like I have in the diagram, we have positive charges moving one after the other, all we'd have to do is figure out what the charges are, so our total number of coulombs divided by seconds, and that would be our current flow. So a current of 2 amps means we have 2 coulombs per second flowing. And if positive charges move, so if we have positive charges, like this diagram, we call that, like obviously flowing positive charges, or another name for it is conventional current. Okay, and if we have normally what we would consider, because we don't normally have positives moving, so what we would do is typically we call our negative, or electrons, or what we consider moving in electricity, like in your plugins and so on. So the negative, the electron charges move normally. That's kind of how we consider it. Okay, so if we're talking about the flow of electrons, we usually say that's our current. But if you ever see the term conventional current, that just means that we have positive charges that are flowing instead of negative charges. And that's pretty much it for current. So pretty easy formula. You can solve any kinds of questions if they're dealing with current or time or anything along those lines. Okay, so what we're going to do is also now we're going to look at sort of how batteries work. So if we have, let's suppose we have 2 plates. Okay, and we're going to have a positive charge. Let's suppose we have a proton or some sort of positive charge, and let's suppose it's going to move across the plates on its own. So based on that, we would know that this would have to be the negatively charged plate, and this would have to be the positively charged plate to get the proton to move across. So then the idea is, well, if we were to charge those plates, we have to hook it up to some sort of power source like a battery. So then the idea is, what would the battery look like? So the symbol we use for batteries, we usually just show like a wire connecting them, and then we put the symbol like that. So the longer line is to represent that's our positive connection, and the littler line is to show the negative part of the battery. Okay, so in this case, if our proton is moving across on its own, it's going to be speeding up as it goes across, then we have to have positive and negative plates, and our battery then has to hook up exactly like I've drawn it. Okay, so if you see diagrams And the reverse would happen. So let's suppose I draw my battery this way, and we're going to hook it to 2 plates like this. Okay, and then let's suppose we put an electron this time in the plates. The question might say, is the electron going to move across? Is it going to speed up? Is it going to slow down? Those types of things. So just based on this diagram, we know that this is our positive, so that means this has to be our positive plate. This is our negative, that has to be our negative plate. Therefore, our electron will be repelled from the negative and attracted to the positive, so we'd get our electron flowing upwards in this case. Okay, so when you're doing battery types of questions, just make sure you know which way the positive and negative is, so you know which plate is positive and negative. Okay, so one quick example. So let's suppose for that last example, our last battery I just drew, so we have an electron moving between the 2 plates. Let's suppose the question then is, how much kinetic energy is that electron going to change or gain if it moves through a battery that has charged the plates with 100 volts? So we're looking for energy, so we could use our formula, our voltage equals energy over Q. So if we solve that for energy, we'd have voltage times Q. So we'd have 100 volts, and the charge of an electron is 1.6 to the negative 19. So we would get 1.6 to the negative 17 joules. Okay, so it's a pretty easy calculation, but this is where the electron volts are going to come in handy. So if we use the same formula, we have 100 volts. Our charge is basically 1 electron. So then we just say it has 100 electron volts of energy. So that's kind of why we use that term. We have an electron moving in voltage, so we end up with electron volts. So it's a pretty good situation to deal with these kinds of questions in terms of electron volts. Okay, our last thing we're going to look at is what happens if we have electrons or protons or whatever moving through an electric field, but they don't start stopped. So normally we'd have, let's suppose we had an electron in the electric field. We know that it's stopped and it's going to speed up, and we could calculate the speed when it gets to the other side of the plate. But in this case, what we want to do is we're not going to have that electron being stopped. So let's suppose the electron started outside the plates and we shot it through a hole into the electric field. So let's suppose the original velocity of the electron was, let's suppose it's 3 times 10 to the 6 meters per second. So we're going to shoot that thing in at an extremely fast speed. Then the question might be, what's its final velocity when it hits the other side of the plate? So when we did these questions before, the shorter way was typically dealing with energy. So we used our change in kinetic energy to help us figure out the final velocity. So we said our normal velocity, or our normal energy was 0. So then we could calculate that like we did yesterday. So the trick is with these kinds of questions is we're going to have to calculate the energy that it has already as kinetic, and then we're going to have to add on the energy that it gains going through the electric field. So let's do this question. So let's suppose I don't have a voltage. Let's suppose we have a 200 volts. Oops. And let's suppose we have 10 centimeter distance between the 2 plates. Okay, so if we were trying to calculate what's the speed that it's going to be, so we know that originally it has a velocity of 3 to the 6, so we can actually calculate the energy, the kinetic energy it has to start with. So we'd have 1/2 times the electron, 9.11 to the 31, and we times it by 3 to the 6 squared. And we get 4.1 times 10 to the negative 18 joules. So we have that much energy that it's moving with before it even touches the plates. So now what we got to do is we got to figure out, okay, how much energy is it going to gain as it goes through the plates. So we need to do that. So we have to use our energy equals voltage times Q. So we have 200 volts times our charge, 3 to the sorry, not 3 to the 6, 1.6 to the negative 19. So we want to figure that part out. So we get an answer of 3.2 to the negative 17 joules. Okay, so we just got to be careful. So in this case, the electron has 4.1 to the negative 18 as it enters. It's going to gain 3.2 as it moves across. So from there, we can now figure out our total energy. That's probably the easiest way to do this one. So our total energy would then be, right, from, it started with that much, it's going to gain 3.2, so we need to add those together. So then our total change in energy, by the time it hits the far plate, it would be 3.6 times 10 to the negative 17 joules. So now that we know that its energy that it is when it finally hits that plate, we can actually calculate its final speed. So we can just do our 1/2 mv squared again, but in reverse. So we'd have 3.6 to the negative 17 equals 1/2 times our mass, once again, times v squared, and solve it for v. So if we take our energy, divide it by 1/2 times 9.11, and then square root that answer, we get an answer of 8.9 times 10 to the 6. Okay, so the only thing that's different about this question is we have an initial velocity to start with. So we just have to figure out what that energy is when it enters the plate, add the change of the energy that it's going to gain when it goes through the plate, and then just work backwards to calculate our velocity. And we could calculate acceleration, time, any of these kinds of questions that we would want. So there's lots of different steps that could be added on. But the key idea is you just got to remember that your velocity goes through. So one more type of question. So let's kind of re-sketch this out. So let's suppose we have a plate like that. We have another one with a hole in it that we're going to shoot the electron through again. But now the question is, let's suppose we want to figure out the speed of the electron entering the plate. Actually, not necessarily the speed. So let's start easy. So let's suppose the electron again. Let's just make up a number here. Let's suppose it's moving at 3.2 times 10 to the 6 meters per second. So in the last example, we had our negative plate here and our positive plate there. So we knew that when it hit the plates, it gained more energy and it actually sped up. So my question then is, what happens if we reverse the charge of the plates? So what happens if the electron moves into the plates where the first one's positive and the second one's negative? So this electron's going to then, as it hits the gap, right, it's going to start slowing down because it's going to want to get attracted to the positive and it's going to get repelled from the negative. So it's eventually, if it's not going fast enough, like if it's going super fast, it might just blast through and just slow down when it hits the negative plate. But let's assume that the voltage is going to be strong enough that the electron's going to eventually come to a stop somewhere in between the plates. So the question then is, can we calculate that? And the answer is yes. Right? The previous question, we added the energies to be able to figure out what the total energy would be at the end. So what we call this one now is we want to figure out how much energy or how much voltage, right, because the voltage is going to slow this thing down, is required to stop the electron. Okay, so we kind of do the question the same way, it's actually a little bit easier. So we still need to know the energy, so we still need to know how much energy the electron had when it hits the plates. So we know our kinetic energy of the electron is 3.2, sorry, it'll be 1/2 mv squared. Let's write that in there first. So we'd have 1/2 times 9.11 times 3.2 to the 6 and we want to square that. So let's do that calculation. And we get an energy of 4.66 times 10 to the negative 18 joules. So that's how much energy it has. So our logic then is that's going to be our change of energy, right? Because the only thing that's different now is we're starting with that, and we're going to end up going to a stop. So our kinetic is going to go from 4.66 to 0. So then our change in energy is exactly 4.66 to the negative 18. So the only thing we got to do differently now then is calculate our voltage. How much voltage is going to give that charge that much energy? So it's a pretty easy calculation. Just put in your answer and divide it by the charge of an electron, and that should give us our voltage. And I get an answer of about 29 volts. Okay, so that means if we hooked our battery, so if our battery was drawn like this, we have our positive and our negative terminals hooked up to the battery, all we need is a 29 volt battery, and that would stop an electron going at that speed. It would eventually come to a stop inside the plates. So quite often what we do is we're going to call this term, whenever we do these kind of calculations, usually it's saying calculate the stopping voltage. So we could have used that as a title, I guess, today. Right. Okay, one last type of question. So we've looked at an electron getting shot into plates. So now the next question is, what happens if the electron gets shot into the plates, but it gets shot in right at the top? So let's suppose we have a 10 centimeter distance between our plates, but this time now our electron is going to get shot in right at the very top of the plate. So instead of coming in perpendicular where it would move across the plates, now it's going to get shot in horizontally. So using sort of common sense is it's going to get repelled from the negative plate and get attracted to the positive plate, but because it's moving in at a certain speed, so let's once again make up a number. Let's use our 3.2 to the 6 meters per second once again. So it's going to get shot in at a speed, and instead of just going straight down to the positive plate, it's going to follow sort of a projectile path. So this kind of question, let's use a voltage of 20 volts. So that's our charge in the plates. And the question then is, where's that charge going to move to? So let's suppose, let's basically say how far, let's look for a horizontal distance. How far will that electron go horizontally before it crashes into the positive plate? So you can see it's basically a projectile question like we did in Physics 20. So we know our voltage, so that's the first part. So really the only thing we need to then figure out is we've got our horizontal velocity, so that's good. We're looking for horizontal distance, so that's good. So the way to do that, remember, we need to use, for horizontal motion, we use our easy formula. So we basically need to know the time. If we know our distance, that's what we're calculating. We know our velocity, we just need to calculate the time. So it'll be 3.2 to the 6 times whatever the time is. That should give us our final answer. So the challenge then is, how do we get the time? So the first step then is, what do we know? So we know vertically, in terms of vertical motion, our VI is 0, just like we did for a cliff question. We know our distance that it's going to fall is 10 centimeters, so let's write that as 0.01. And we don't know VF. We're looking for time, that's our challenge. We don't know VF, and we don't know acceleration. So we're going to have to calculate one of those first. Let's do this question by calculating acceleration first. So normally with a gravity question, a projectile question, we know acceleration is 9.81, so we can plug all the information in to solve for time. So the same sort of thing works here, but we have to calculate the acceleration first. So how do we do that? Well, we're going to use force equals mass times acceleration. So acceleration will be force divided by mass. What's force equal to? We know from our other formula it is electric field times charge divided by mass. But do we know the electric field? No. We know voltage and we know distance. So our electric field will be voltage over distance. So I'm just going to write this as sort of one long formula. So we'll have voltage over distance times Q divided by mass. So you can see really the only thing that's different with this question is we have to use our new formulas to help us solve for acceleration. The other option is we could maybe possibly solve for VF like we just did with our previous example. So we'd use a VI of 0, we'd use our voltage, calculate the speed it's going to be when it hits the bottom. But let's do it with acceleration just because it's a little bit of a different approach. So our voltage is 20 volts divided by 10 centimeters. Our charge of an electron is 1.6 to the negative 19. And mass of an electron 9.1 to the negative 31. So we can do all that to solve for acceleration. Okay, so we do that calculation, we get 3.51 to the 14. So it's a pretty large acceleration, but that's okay. We're going to get numbers like that. So now if you remember back to Physics 20, how do we calculate our time? Well, we're going to use distance equals VIT plus 1/2 AT squared. Our VI is 0, which makes things nice. That goes away. So we're basically just going to solve for time. So we'd have 1/2 times 0.351 to the 14. And we just need to do that. So 0.01 divided by that. And we're going to square root our answer. And we get a time of 7.55 to the negative 9. So extremely fast, which makes sense. If it's accelerating that fast, we've got strong plates, not very big distance, so it's going to happen almost instantly, but it will follow the path of our projectile. So you can see then in this case, we've got our time, that's what we want to plug in here, so 7.55 to the negative 9. And we're ready to calculate our horizontal distance. We want to take that answer, times it by 3.2 to the 6. And we get a distance of 0.024 meters, which would be 2.4 centimeters. Okay, and use some common sense. If our original gap was 10 centimeters big, yeah, we're in the right ballpark, right? It's because we got such a strong voltage, it's going to get zipped downwards, and it's only going to go 2.4 centimeters before it collides. And that's it. So there's lots of these kinds of questions where we're going to be using new stuff, old stuff, a little bit of projectiles for these kind of weird ones, and that'll lead us into future units as well. So that's all for today.